And now for the consequences of that big theorem. The Pythagorean who came up with this proof, or something like it, was named Hippasus. He was very excited by this clever reasoning and shared it with the others. Pythagoras, however, was very unpleased. Hippasus had proved that the numerology was wrong. Not everything could be described by the relationship of whole numbers. So, what did he do? Well, on the next sea voyage that the Pythagoreans undertook, Hippasus fell overboard and drowned. Or was he pushed? He was totally pushed. They killed him. Furthermore, Pythagoras forbid any of the Pythagoreans to speak of what happened. Not the murder, but even more than the murder, not the mathematical proof. He tried very hard to find a flaw in it, but he could not. And therefore, he denied that it even existed and wouldn't let anyone speak about it. In fact, he called these numbers irrational numbers, which can both mean not a ratio, but in the ancient Greek it could also mean things of which we do not speak. Now, one Pythagorean, sometime later, told his wife about it, and shortly thereafter, he drowned at sea. Now, this time it was just an accident, but the Pythagoreans all felt that there was some divine justice at play. Eventually, however, because secrets are, they don't stay secret if there's more than one person who knows them, word got out among the Greeks that it became common knowledge that there were numbers out there that could not be written as fractions. This disturbed the mathematicians greatly. They didn't want to work with approximate numbers. They didn't want to just be fudging around with things. They wanted to work with absolute truth. That was what appealed to them about mathematics in the first place. Proving things, knowing the absolute truth. How could they pretend that they knew about mathematics if there were numbers that they could not even write down, numbers that they didn't properly know or understand? Well, this bugged them for a long time, but eventually the solution came at the hands of a mathematician named Eudoxus. Eudoxus from the city of Cnidus. He was born sometime around 410, 408 BC and died somewhere around 350 BC. What he did was he represented numbers not as a relationship of two whole numbers, like a fraction, but as the relationship of two lengths of lines. For example, suppose we put two squares next to each other like this. This is a square, this is a square, exactly, two squares in a row. Instead of saying the number 2, or 2 over 1 if you want to write it as a fraction, we could say the relationship between AC to AB, or just AC is to AB. What is the relationship of this whole line to this whole line? Well, it's twice as long. Okay, so instead of saying 2, it's almost like they're saying twice. And instead of saying 1/2, they would say the length AB relative to AC. What is AB to AC? It's 1/2 as long. Now, not only can you represent any whole numbers or fractions in this fashion, but that number d, such that d squared is 2, well, d was the diagonal of a square. So you just say AE relative to AB. If this is 1, then this is the square root of 2. And so you can say with exact precision, what is the square root of 2? It's the relationship of this to this. Now, this is a little bit convoluted, but it enabled them to speak once again of exact, precise truth. They can't necessarily write it out as a number. They've abandoned numbers. Numbers, it's going to take the Arabs to kind of bring numbers back into mathematics. Because inspired by this, the Greeks translated all of their mathematical discoveries into this format. They started doing all of their work with geometry. And the end result was a masterpiece of human literature called The Elements. We generally give Euclid credit for this book, but there is some evidence that there was a book called The Elements that was a geometry book even before Euclid was alive. Anyway, this geometry book, and if you want to rate it by how many copies have ever been published, it is second only to the Bible. This has been read by so many people for over 2,000 years. It was written about 300 BC and is still useful and inspirational today. Well, but what about this number d that squares to be 2? What do we do with it? Well, today we use what I consider a complete cop-out. We basically say it's the number that squares to be 2, or we say the square root of 2, and we write it as this. But if you look at this really closely, it doesn't tell you what the heck this number is. This is just a symbol abbreviating the number which squares to be 2. In other words, we don't really know what this number is. We are just using a symbol to represent it. It's like if I said, oh, what is who is the fastest person on Earth? And I just say, oh, I refer to him as Mr. Fast Guy. Oh, come on. I want his name. I want to know how I can find this person. No. What is the square root of 2? Well, this is just a symbol for it. Okay, granted, you can plug it into a calculator, and you can get a whole lot of decimal places of accuracy. But, ... we're not getting all of it. For all we know, maybe it starts repeating. For all we know, maybe it stops. No, we know for a fact from that proof that it does not ever repeat. It does not ever stop. It is not a fraction. It is an irrational number, a real number that is not rational. And to this day, we don't have a way of writing it out entirely. We can approximate it. We know properties about it. We know that when you multiply it by itself, you get 2. That can be very, very useful. But to this day, we still haven't really overcome this problem. This number is not a fraction. Its decimals go on forever. And, well, that's the problem. And that's where it stands right now. We use a cop-out. I hope you appreciate that this is a cop-out. And that someone once lost his life for this.